here with these dice. And yesterday, right at the end of class, I said, okay, let's get our chart set up. This is our sample space, is the official vocabulary, but all the possible outcomes when you roll a pair of dice. So the first question is the probability of a sum of 5. Thoughts? I guess I better stand over here. On the probability of a sum of 5. I think we kind of talked about how many there were before we even did the chart. How many sums of 5 are there? How many?
1, 2, 4.
One, 2, 3, 4.
Yeah, I got it right.
Out of?
36. 36.
Out of 36.
36.
What do we know about 4 out of 36? Reduces to be 1/9. Okay. Now, B, sum that is an odd number. So probably that the sum of the dice is an odd number. Thoughts?
50. What?
Don't be just shouting out everything now.
Isn't it 6 out of 36? 6.5?
I just put that up on it.
I would have said more than that.
50%. Oh, 18 out of 36? Right, I know.
Was that what you were saying?
Yeah. Okay, so if we're going for sum that is an odd number, we already had these that added to be 5, yes?
3 and 4.
Okay. We also have, what else adds to be odds?
Those, and then you skip them.
1 and 2, 2 and 1 add to be 3, yes? So we already have these. What else?
6, 1,
Oh,
5,
boy.
2, 4, 3, 3, 4, 2, 5.
All your 7s. And? Are you catching a trend here?
It's diagonal.
Yeah.
Like
All the 9s
what's that?
and the 11s, yes? So that's how many? Should be half of them, right?
18.
Okay. Should be half of them, which is 18 out of 36, 1/2, 5/10, 50%, all of that, right? Okay, C. Sum that is less than 4.
1, 1, 2, 1, 1, 2, 3, and that's it.
3 out of 36.
Upper corner.
Just those?
So less than
I guess.
4.
Yeah, it says less than 4. Valid point. It doesn't say less than or equal to 4. Less than 4, so we've got 3 of them. Out of how many choices?
36.
What is 3 over 36 reduced to be? 1/12.
Because 6 times 6 is 36. What?
Okay. Now, okay, D. We've been working our way up to D and E. The probability the sum is greater than 9 or the numbers are the same.
So
So what do we know about greater than 9?
very nice. Everything past that little 5445 right there.
Okay.
It's got to be below that on the
6,
right.
4, 5, 5, 4, 6.
And yep, there you go. And very nice. Same number.
Are you guys seeing? Okay, so how many do we have that are greater than 9? Have a sum
6.
greater than 9.
6.
That's 6 out of 36, yes?
Yep.
What about numbers are the same?
3, 3.
Okay.
6 because
So-
there's 6 numbers.
If we look at numbers are the same, 1, 2, 3, 4, 5, 6.
Mhm.
Okay. What's the catch?
They're the same.
We had 2 that overlapped in both categories, yes? So what do I need to do with those 2? Since they're overlapping, we're going to subtract them off.
Off 6 out of 36.
Well, off of these two together. So the idea here is, okay, and I'm kind of taking the long way. Some of you guys have an answer going a little bit shorter way, but I need the concept here, is that we had 6 that were greater than 9. That's the first 6 out of 36. Then we had 6 where the numbers are the same. That's your 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. However, when we counted those 6 and 6, how many pairs did we double count?
2.
There were 2 pairs we double counted, and so that's the 2 I'm subtracting. Okay? So what is 6 over 36 plus 6 over 36 minus 2 over 36?
10 over 6.
10 over
36.
36, which is what? Reduces to be 5/18. Now, could you have just counted up how many pairs were included here? It is possible. Again, there are times that the easy, shortcuts work. There are times where we need to understand the concept behind it, which is why you see why I went through it. But if we just count these up without overlapping these two, it does add up to be 10 of them out of 36. Okay? So right there, this is the idea of those two events were not mutually exclusive. Okay? They overlapped, and so they were not mutually exclusive, and when that happens, we have to subtract off any overlap, which is what we were doing up above with the area yesterday. Okay, one more. Probability the numbers are different, or the sum is less than 6. Notice it's an or again. Numbers are different.
Oregon.
How many of them have numbers that are different?
Every one but 6. 25. 30.
Okay, can we work smarter, not harder here? Okay, if 6 of them had numbers that are the same, how many have numbers that are not the same?
30. 30.
30. How about sum less than 6? How many have a sum less than 6?
Less than 6. Everything right there till 5 and 4, or 5 and 5.
What are we?
That diagonal line right there.
This is 5. This diagonal is 6. So okay. So 1, 2, 3, 4, 5, 6, 7. Wait. 8, 9, 10. Did I count that right?
2, 3, 9, 5, 6.
Yeah.
I'm sorry. I got that.
Yeah. Now, are there any that are going to overlap here?
Absolutely.
Yeah.
All of them.
Not all of them.
No, not all.
How many do I have to subtract off that are overlapping?
1, 1.
1, 2.
And 2, 2.
Right. How about those actually are the ones, 1, 1, and 2, 2 are actually the ones we get to keep? Because the probability is numbers are different.
Yeah.
So of these 10 numbers that were different, or excuse me, of these 10 pairs that had a sum less than 6, how many were different? All but the 1, 1, and 2, 2, yes?
Oh, so minus 8.
So we're going to subtract off 8. 30 plus 10 minus 8, all over 36 is going to give me?
32 over 36.
And 32 over 36 reduces to?
2/3. Or no.
4 over.
Oh, no, I did that completely wrong.
I like 8/9. Divide by 4?
That's what I was thinking. Dave and Buster.
Okay, so I wanted to go through this. One, make sure we kind of understand these two examples at the bottom are examples of not mutually exclusive because their two sample sets were overlapping. Okay, when they don't overlap, then we can talk mutually exclusive. But those bottom two were examples of not mutually exclusive, and thus we are subtracting. Okay. Okay, we have what we need. We're ready for the next page. as we move into the next page, we're going to talk about being able to identify independent events. Okay, whether or not two events that happen back to back are independent or not. Okay, so, and I don't know that we're actually going to find these probabilities, more just talk about whether or not they affect each other and how you would find the probabilities here. So, in this top half, a jar contains 12 green marbles and 8 violet marbles. First scenario, a marble is chosen at random from the jar and replaced. Another marble is then chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes for the second marble? Now, the first scenario I'm going to use to explore this is, okay, what would be the probability of drawing a green marble and then drawing a violet marble? Okay, so individually here, one at a time. What's the probability of drawing a green marble?
12, 20.
Why?
Because there's 12 and 8.
Okay. Okay. So there's, for green, there's 12 marbles out of a total of 20 marbles. Now, after you draw that green marble, what did the scenario tell us? You replace it. Yes? So now, what's the probability of drawing the violet marble? I drew a green marble. What I do, I put it back. I'm now drawing a violet marble.
8, 20.
There's 8 violet out of
20.
20 total marbles. Okay. Now, and I guess we can. So when I looked at the book, really the problem was just a matter of, we were trying to figure out, are these independent or are they dependent? Are they affecting each other? In this case, did drawing that green marble affect my chances of drawing a violet marble?
No.
No. Okay. When we talk about independent marbles, and I said, or independent situations, okay, you're going to take these two probabilities, and in this scenario, you will be multiplying them. And let's see. I remember how the notes go. We'll be working on that in the back page. Now, what I will say is if you have a situation like this and you go to multiply them,
Can you simplify first?
I would definitely simplify first. I wouldn't even hesitate because 12 20ths is what? Three-fifths. If you divide by 4, 8 20ths is 2/5. I can now multiply without picking up my calculator, right? What is 3/5 times 2/5? 6 25ths. Okay? Now, that was your green and violet. What if I change this up and this probability of drawing a violet and then another violet?
8, 20, 8,
So what's the probability of drawing the first violet?
8, 20.
8 violets out of 20 marbles. What's the probability of drawing a violet on the second time?
8, 20 because you replaced it.
Okay, and again, the key is, this is a replacement scenario, so it's 8 out of 20. Okay? When you draw one, then the next, we are multiplying these. Okay? Two things back to back, we're multiplying. What is 8 20ths reduced to?
2/5.
2/5? What is 2/5 times 2/5?
420. 5.
4 25ths? Okay. Now, the big question was, does the color of the first marble chosen affect the possible outcomes for the second marble chosen? And in this case, what is that overall answer then?
No.
No, it does not, because, and what's the main reason?
You replaced the model.
Because there was replacement there, yes?
Yes.
So this is an example of These would be considered independent. Okay. They are independent events. Replacing the marble means the first draw does not affect the second draw. Okay. Time to switch it up. On B, a marble is chosen at random from the drawer and not replaced. Another marble is chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes for the second marble chosen? And you're already nodding your heads, saying yes. And why is it going to?
Not replaced.
Because it says not replaced. Now, let's go through and look at how it does affect the probabilities. You're saying it does affect. Good, I agree. Okay, probability of drawing green then violet.
12, 20.
Okay, so probability of drawing the green is still 12 out of 20. What about probability of drawing a violet here?
8, 19.
Do we agree? How many violet are there? 8. How many total marbles are there now? Only 19, because what do we assume we did the first time? It was the probability of drawing a green. So we're going to assume we drew a green. Okay, we assume there's one less green in the mix, and so there's still 8 violet marbles, but it's only out of 19. Okay.
8 plus 8 is 9.
Again, it would be multiplication. I would still reduce. What does 12 over 20 become?
4 over 5, or 3 over 5.
I'm going to say not 4.
Yeah, I'm missing it. Sorry.
3 over 5. What does 8 over 19 become?
8 over 9.
8 over 19. Okay, unfortunately, that whole 19 throws a kink in things.
24.
Kink.
24 over what? Okay. 24 over 95.
Drop line.
Okay. What about violet then violet? How does this change things up? So what's the probability of drawing the first violet?
8 over 19.
We're restarting the problem, fresh problem, so 8 out of 20. We're back to having all 20 marbles.
7 over 19.
And then what do we assume? The first probability was of drawing a violet. So we're going to assume we drew a violet. And then we did not replace it. So now what are we at?
7 over.
Instead of 8 violets, there's only 7 violets. Instead of 20 total marbles, there's only 19 total marbles. So that would affect both your numerator and your denominator, right? Let's see. 8/20 is not 3/5. It is 2/5 times the 7/19, which is 14/95. Okay. In this case, we already answered this. I'm just going to write it down. Does the color of the first marble chosen affect the possible outcomes for the second marble? And that is definitely yes. These are not independent. You could also say that they are dependent. And that's because not replacing the first marble affects second marble. I'm trying to be short about that, but okay.
Okay.
get what you need there. And then the bottom is pretty much the same. I think I'm going to honestly use them as, let's do the probability and check the make sure we know how to do the probability. And I'm probably not going to write out the explanation on the bottom piece, but Aaron, behave. Okay. There are 10 cards in a box, 5 black, 5 red. 2 cards are selected from the box, one at a time. Scenario A. A card is chosen at random and then replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? Explain. Is that going to affect? Does the color of the first card drawn affect the color of the second card drawn? And that is I'm just going to put a no here. It does not affect it, right? And I'm trying to save time is what I'm trying to do here. So, probability of red than black. What's the probability of drawing the red card? 1/2. I'm going to start with it's 5 out of 10, but I do agree that'll be 1/2. Then, what's the probability of drawing a black card?
5/10.
Well, wait.
It's
Since you
replaced.
threw, wait.
It's replaced.
Effect. Wait.
Oh, yeah, my bad.
Okay.
And then replace. So yeah.
Watch that keyword, right?
Yep.
Okay. This one is replaced, so all 10 cards are back, and there are 5 black. So 5/10 is also 1/2. 1/2 times 1/2 is
1.
4.
1/4. Good cover up. What about red than red? Probability of your first red. 5 out of 10 or 1/2. Probability of the second red?
1/2.
Because the first red card got put back, right? So I've got all the cards there. So that is another 5/10 or 1/2. 1/2 times 1/2 is again 1/4. Okay. Other piece. A card is chosen at random and not replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? The answer to that piece is, are we going to have the first one affecting the second one this time? Yes, we are. Okay. Let's check these probabilities real quick. Make sure you know what you're doing. Probability of the first red card is what? 5 out of 10. Probability of then drawing a black card. Okay, so we're going to assume we drew a red card. We're still holding the red card. So now, instead of drawing from 10 cards, I'm only drawing from 9 cards. But that first card I drew was red, so are all the black ones there? Yeah. So 5 out of 9. Now 5/10, I would go ahead and say 1/2. 1/2 times 5 ninths?
6 over 18.
I'm going with 5.
I did the same thing you did, Aaron.
1 times 5?
Adding them like
I did the same thing, so I had my answer as 1/3.
Okay, I'm going to say get the silly mistakes out of the way now. That way you can ace solve us, right?
Yeah.
Okay, what about probability of red than red? Probability of the first red?
5/10.
Back to the beginning, 5/10. Probability of drawing a second red
4/9.
when the first red's not replaced.
4/9.
So now instead of having 5 reds, I'm down to 4 reds. Instead of having 10 cards, I'm down to 9 cards. So if you want to reduce, 1/2 times 4 ninths. What do you want to say here?
4 over 18.
Okay. What about 4 over 18?
Reduce.
Reduces to? 2 ninths. And this is where I would say we could have cross-canceled the 2 and 4 back here. Okay. top of the back page really just kind of talks about what we ended up doing here. So my original plan was not actually to find these probabilities, but they're actually multiplying, but we did. So that's all right. The idea, if you have two independent events, okay, you're finding those two probabilities, you are multiplying them, which is what we just did on that page. Independent events, when the outcome of one event does not affect the probability of a second event, the two events are independent. Not sure we really need this example here, but still good basic probability review. When rolling a die and tossing a coin, the result of the die roll and the result of the coin toss are independent events. Because what you roll on a die, is that going to affect what you get when you flip a coin? Yeah.
No.
Rolling the die, flipping a coin, two totally independent things, okay? Now, make sure we know our probabilities. What's the probability of rolling a 4 when you roll a die?
We're on 1 out of 6.
Okay, there's 1 4 out of 6 options. What would be the probability of, when you flip a coin, getting a heads?
1/2.
Because your options are heads or tails, right? So 1/2. How do I find the probability of rolling a 4 and tossing a head? We're going to take these two probabilities and multiply them. 1/6 times 1/2 is 1/12. Okay, so it is a multiplication thing. Okay, we're going to talk about Alex's wardrobe. Alex's wardrobe is a color up on mine, which is going to be important for some of the questions. So, I'm not sure, and I'm really not sure if this Alex is a boy or a girl.
Thinking girl.
That was kind of my thought.
Well, it's kind of, you got a V-neck in there.
Yeah, but check out that third yellow one.
That's what I'm
Yeah.
saying.
I don't know.
That red or yellow?
To each their own, right? Could be either or.
That red or shirt.
Okay, now, okay guys, information provided.
Or purple.
2 pieces of important information. Alex cannot decide which shirt today, so she chooses one shirt at random. Those are your shirt choices in the picture. You might write on your paper what color they are, so when you look back at it later, it makes sense. Now, the other option, or the other piece of this problem, the probability of rain today is 40% or 2/5. Question A. What is the probability that Alex chooses a yellow shirt and it does not rain today?
That's got nothing to...
Sometimes you pick your wardrobe based on
Right, no. But
whether or not it's supposed to rain today.
like,
I got it.
So, what are we thinking here?
I did 1.5 times 3 over 5.
Okay. And what this is asking, realize, is this was the probability of yellow and not raining today. Probability of yellow. 4 shirts to choose from. 2 of them are yellow, yes? So 2/4, or as Landon is saying, 1/2. Now, the good key. I can't 100% say it works, but usually when you see the word and, we're going to multiply. These are 2 independent events. First one does not affect the other, but they are one after the other. Okay? So, and probably it's not going to rain. Well, if 2/5 chance of raining, what's the probability of not raining then? The other 3, right? And so 3/5 does not reduce. What is 1/2 times 3/5? 3/10, which, based on the fact they gave us percent, I'm not sure what form they would want. Realize, what is 3/10 as a decimal? 0.3. What is 3/10 as a percent? 30%. So if I review a little bit like I did yesterday, any of those 3 could be possibilities, right? Okay? Now, what is the probability that Alex chooses a yellow shirt and it does not rain today, or that Alex chooses a green shirt and it rains today? Okay. What?
We just did answer one of them.
Okay, we just did one of them, didn't we? Because the first piece is probability of yellow and not raining. And we can definitely steal our answer from above. And then it says, or what? Probably that Alex chooses a green shirt and it rains. Now, notice these events here. Well, and here's the easiest thing to look at. What's connecting these scenarios? It's or. What's the probability of one or the other happening? Which means once we get these two probabilities, we are just going to add them. Okay, so we're combining the pieces here. Now, we already said yellow and not raining was 3/10 from above. Not going to waste my time redoing that one. Have you figured out the probability of a green shirt and that it rains?
Not yet.
What's the probability of green? 1 green out of 4 shirts. What's the probability that it rains? Giving us 2/5. What is 1/4 times 2/5? 2/20, which reduces to be 1/10. So what are we going to be doing here? 3/10 plus 1/10, which is 4/10, yes? I wonder if they want percents on this section because I have another percent written down. What is 4/10 as a percent? That is 40%, yes? Okay. Now, well, I definitely, because I didn't reduce 4/10 in my notes, so I'm guessing I definitely was thinking percent here. Okay. It's also 2/5. It's also decimal point 4. Okay. 2 more scenarios here. Gotta move. First of all, we have a spinner. You spin the spinner 2 times. Assume the probability of the blue each spin is 1/3, and the probability of orange each spin is 2/3. So notice they're labeled B and O. So probability of blue is 1/3, probability of orange is 2/3. What's the probability of getting the same color both times? So if you spin the spinner twice, so probability of getting the same color both times, that means we want to investigate what? The probability of getting, what's one option we could need to look at?
Orange.
Orange then orange. So if I say probability of orange or O comma O, trying to be quick. What's the probability of getting orange the first time? Two-thirds. What's the probability of getting orange the second spin? It doesn't change, does it? So what's the probability of getting orange followed by another orange? 4/9, right? They're 2 separate turns followed by another. So 2/3 times 2/3, 4/9. So that was getting the same color orange back to back. What's the other option you could get? So the probability of getting blue back to back. What's the probability of getting blue on the first spin? 1/3. What's the probability of blue on the second spin? 1/3. These are independent. They do not affect each other. 1/3 times 1/3 is 1/9. Now, what do you think we need to do here to finish this up? We're going to add them, okay? If it's probability, what's the probability of getting the same color both times? So what's the probability of getting orange followed by orange? Or what's the probability of getting blue followed by blue. So we are adding 4/9 plus 1/9 is 5/9. And I just have 5/9 on my paper. Realize that could be turned into a decimal or percent where necessary. Okay, I threw this one in because there's one in the homework similar to it. And so I wanted to kind of get your brains thinking on it. So, the example I put in here, a city issues 4-digit license plates for motorized scooters. The digits 0 to 9 are chosen at random by a computer program. What is the probability that the license plate meets each set of criteria? So, now, the first one is on the easier end of this. What is the probability that the 4-digit number is odd? What is the probability in general that any number is odd?
50%.
50%? 1/2? And so if and here's the deal, this is a 4-digit number, right? But all that really matters is the last digit, right? That's going to make something even or odd. Well, you could have 0, 2, 4, 6, 8 making it even, or you could have 1, 3, 5, 7, 9 making it odd. And so we are going to say, I would just go as basic as 1/2. Okay. So 1/2 or 0.5, I think they'll accept either right here. The first number is not 3.
8 out of
What?
8 out of 9. 8 over.
No. No. Well, wait, yeah.
Wait, they're oh 0 to 9, so it's okay.
Okay, so what's the trick we have to watch here? Use your fingers if you need to. How many digits are 0 through 9?
10.
That's 10, yes, because 1 through 9 is 9. You guys have learned this trick over time, maybe? And so this right here, realize, is 10 digits. So when you're looking at the first number being a 3, all that really matters is that number right there, yes?
Mm-hmm.
First number is not 3, so how many numbers are not 3? That's 9 of them out of how many total numbers? 9/10. So that's 9 over 10 or 0.9. Okay, we're getting it. Probability. The first 2 digits are the same. What do we think?
2 out of 20.
Two out of 20.
No.
110. You said 5, right? 100. What?
Not.
You said 100. I thought I had all the answers.
Okay, wait a minute. I'm trying to, because, okay, I got it. If this is a 2-digit number, how many options are there for the 2-digit number?
20.
No.
Wait. If it's
Almost 99.
100.
100. Because 1 to 99 is 99 numbers, right? And that 1 could be 0, 1. But also, besides 0, 1, you could have a number in this scenario of 0, 0. So the idea of there are how many 2-digit numbers if you're going from 0, 0 to 99?
10.
No.
No.
That's 100 2-digit numbers. This is the probability that the first 2 numbers are the same. So those options could be what?
1, 1.
0, 0, 1, 1, 2, 2, 3, 3, 4, 4,
10.
all the way up to 9, so a total of 10 of them.
Oh.
And what is 10 out of 100?
110.
110. Sounds like he's already done the homework problem. Okay. All 4 digits are the same. That is going to be 10 out of
10 out of a million.
10,000 choices.
I put 40.
Okay. That would be 10 out of 10,000 choices. Do the homework for tomorrow. That becomes 1 out of 1,000 or 0.01. By the way, trash ball. If you earned extra credit, I forgot to put those on the test, so I will be going back to do that.